Thank you everyone for joining this webinar. This is American Society of Mechanical Engineering, or ASME, webinar on cybersecurity in manufacturing. So this is organized by the Computer and the Information Engineering, or CIE division within the ASME. So the CIE division, probably people didn't hear that, has been actually existed for over 40 years. So 40 years ago, it was formed by a group of researchers in academia and as well as industry practitioners who are interested in computer or computational techniques and their applications in mechanical engineering domain. So since then, there are a variety of research topics such as computer-aided design, manufacturing process design, modeling and simulation, artificial intelligence, and knowledge engineering. And of course, now they were heard about machine learning, which it was not a new phenomenon, as well as virtual environment like augmented reality, virtual reality, visualization. So given the increased complexity of manufacturing systems nowadays and the use of new technologies such as sensors, for instance, as well as IoT, the cybersecurity becomes a very important topic within a CIE. So that's the reason CIE division, and led by the division chair, Professor Jitesh Panchal, and decided to organize this webinar series. And hopefully this will help our students, researchers to understand the subject and gain more research interest. The CIE divisions also organize the annual IDTC CIE conference every August. So you can see the background of the camera, which is the IDTC CIE. So each year we had this, we're going to call for a paper, and the paper will be due roughly early February. The conference is going to be, next year conference will be virtual as well. So if you have interest for this topic and cybersecurity for manufacturing, please submit a paper. So we're going to have special sessions over there too. So today's webinar and will be hosted by Professor Jitesh Panchal. And Jitesh is a professor at Purdue University. He directs the Design Engineering Research Lab. As a matter of fact, his research also includes security in cyber physical systems application in design and manufacturing. And he's gonna give a talk probably later in the series. And so today, and Jitesh is gonna introduce our two speakers. Thank you.
Thank you so much, Ian. Thank you all for joining, and particularly thank you, Mark, and thank you, Nikhil. Sorry, I'll just use your first names here. It's really nice to have both of you here as the first two speakers of our series here. We have been following your work for some time now on this area of additive manufacturing and security in manufacturing systems. And one of the key things that, that struck us in terms of your research is you have taken a holistic view of security in design and manufacturing. So we thought it's a wonderful idea for you to come and share your vision about where this new area is leading. So again, I really appreciate you joining us today. So the way we're going to do this is we'll first start with Dr. Mark Yampolskiy. And the title of his talk is Additive Manufacturing Security, Welcome to the New Frontier. So Dr. Yampolskiy is an associate professor at Auburn University in the Department of Computer Science and Software Engineering. He's also affiliated with the Auburn Center, Cyber Research Center, and the National Center for Additive Manufacturing Excellence. He was among the pioneers and is one of the leading experts in the field of additive manufacturing security. And his research interests include cyber physical means of attack and defense in additive manufacturing. And the second speaker that we have for today is Dr. Nikhil Gupta, who is a professor of mechanical and aerospace engineering at New York University. He's affiliated with the NYU Center of Cybersecurity, and his research program is focused on additive manufacturing, including security and manufacturability of products, machine learning methods for materials characterization, and lightweight composite materials. Dr. Gupta's research interests on additive manufacturing security are supported by National Science Foundation, Secure America Institute, as well as industry. And he's an author of over 205 journal papers and book chapters, and he's an inventor of 4 US patents. And he serves on the editorial board of a number of journals, including composites, part B, materials performance and characterization, and material science and engineering, part A. So welcome to both of you. And I will unshare my screen here so that we can have the presentation. So please feel free to share your screen, Mark.
Thank you very much for the invitation. And can you see this?
Yes.
Can you see my screen? Okay.
Yeah, it's coming up.
Open in full mode.
So
and I appreciate invitation. Yeah. Go ahead, please.
If there are any questions that the audience has, please put the questions in the chat window so that we can take those questions at the end of the presentations.
All right. I will start and I will move on right to the slide number 1. And I want to show a short video that demonstrates some research that I conducted together with my partners from Israel and Singapore. And it is a fairly realistic attack. It is a stage attack, but it is an attack that we tried to go from the entire chain of attack. So we start very classical with cyber attack, with spear phishing attack. We prepare emails with malware, and we are sending email to victim and trying to convince the victim to download and open an attachment. And this is a zip file. And if you are familiar with cybersecurity statistics, this is still one of the most common ways to compromise systems, spear phishing. And on the attacker side, we are preparing to, we are starting command and control server, and we are waiting at the moment when victim opens an attachment, and after attachment is opened, exploit start working, and we on the attacker side get remote control to the computer. So we search what files are on the system, we find propeller design file, and we find this interesting, so we download this design, and we are starting manipulating this design file. So what is not shown on the video, but was also something very important, we actually experimentally verified how this modification, what effect this modification will bear in the lab. And after we are done with our preparations, we upload file back and waiting till victim will start printing the design. So this is printing propeller. We printed 3 propellers with original design and 1 with compromised design, and you see markings on the propellers so that we could distinguish which is which. And we flew this for a couple of minutes. And like I mentioned before, we specially crafted that attack in the way that it will bear results after a very short period of time. So as you see in this video, after some period of time, propeller broke and this drone fell to the ground and was irreparably damaged. So this was, like I mentioned, a staged attack. But why should we care? And there are multiple reasons why we should care about. Among others, that additive manufacturing is currently used also to manufacture functional parts for safety critical systems. The product example is GE LibJet engine or fuel injection nozzle for LibJet engine. But we also need to care because many manufacturers considering additive or Industry 4.0, additive is often considered to be integral part of Industry 4.0 as next step in the evolution. Also, it's probably a very well-known fact that the economic revenue from manufacturing in the United States is about 6 trillion, what is 30% of the entire GDP. And this is not surprising that about 35% of cyber espionage attacks are targeting specifically manufacturing sector. What was surprising to me reading this report is that 73% of all manufacturing companies are small or medium companies. They have 20 or less employees. And this is not exactly the size of the company that can invest heavily in the security or cybersecurity of the company. And the only conclusion I could draw that it is not the matter of if, it is really a matter of when we will see real attacks on additive manufacturing systems in the wild. So this area is fairly new. I started working in this 2013, first publication 2014, so I was lucky, one of the first ones in the field. Basically 2013, 2014, there were only a handful of publications. By the end of 2017, 67. Less than 2 years ago, this number has doubled, and I didn't have time to calculate newer statistics. But what is really important to understand is that this research in this area is not limited to the United States. There are at least 14 countries, at least in the 2019 it was 14 countries, meanwhile it's probably more, who have researchers interested in this area. This means that sooner or later, among these countries will be countries that are adversarial to us, and research that is published will draw attention of criminal enterprises or some organization who can monetize various kinds of attacks. So if we talk about security, we really need to think about security threats. Okay, I like to define security threats as something that is achievable and at the same time on the intersection with adversarial goals and objectives. And so far, 3 categories have been identified. It is theft of technical data. Many people refer to this as intellectual property theft. I think that it is a subcategory of technical data theft because not everything is protected, sometimes by organizational reasons, sometimes because the legal framework is not capable of protecting everything what you would like to protect. Next category where I am spending most time in my research is sabotage attacks, like in the video that I showed at the beginning. And the last but not least is manufacturing of illegal parts. And this is a fairly fuzzy category where you can see illegal part manufacturing like infringement or manufacturing of parts like components of explosive devices or similar. So we can look at all the categories from both perspectives, from attacker perspective and from defender perspective. And I highly recommend to look at this from both perspectives because you cannot really attack system effectively unless you understand how defense mechanisms work, and you cannot really develop effective defense mechanisms until you understand how the system can be attacked. So let me just give you a couple of examples. One of interesting research, and obviously there are more than I can show in this short time, but one of the interesting research comes from University of California in Irvine. And they have identified that in FDM, or fused deposition modeling 3D printers, you have a set of motors, 4 or 5 motors. They are responsible for movement along X, Y, and Z axis and for extrusion of filament. And they identified that you could distinguish between these motors based on some characteristic like imperfection in design. They produce different acoustic emanations. And you could also distinguish between the direction of movement and speed of movement based on the frequency domain. So they generated a model how this acoustic emanation can be, after acoustic emanation are captured, how to recreate designs that was printed. So they evaluated this on a fairly simple design, but this was, to my knowledge, the first work on side channel attack in 3D printing. Side channel attacks have been known in different areas, but this was in 3D printing. So they looked at the model, and based on the acoustic emanations alone, they could achieve about 80% accuracy in recognition which axis was moving, X, Y, or Z. and about 18% of error for the distance. Okay, obviously this is something what is very impressive. I would also argue that this is interesting result, especially if you are doing intelligence work. This might be a very interesting result, like what particular country is doing with additive manufacturing or 3D printing, or what your competitors are 3D printing. This is, however, not the result that I would assume sufficient or consider sufficient for infringement of a part. So we need to keep this in mind. Another attack that I'd like you to talk about is coming from my team. And the reason for this was that in additive manufacturing, especially in metal additive manufacturing, one of the challenges is how to ensure the quality of a part. One of the current ideas is to use in situ monitoring and integrate in situ sensor monitoring sensor information in a way of control loop, feed forward or similar, to adjust manufacturing parameters to ensure that part quality is as it's supposed to be. What we have looked at, we actually looked at whether this in situ monitoring can be used as a way to attack the system, a way to sabotage part. And obviously, okay, what we have looked at is infrared thermography that has assessment of melt temperature, and we looked at the ability to and effects of changing the temperature estimate. We conducted a couple of experiments. Basically, we provided false sensor readings, and in control loop, it caused adjustment of the power density on the laser. We tested this on powder bed fusion machine, laser powder bed fusion machine by my collaboration partners from Lawrence Livermore National Laboratory. And on the graph below on the right, you could see optically A is how it should be, B, C, and D, these are different kinds of attacks, different kinds of effects from attacks that have been conducted. So even if you are not familiar with material science or don't understand what effect it can generate, you will see just visually that it bears results that eventually will translate to degradation of mechanical properties. A couple of years ago, my collaboration partners and I spent a significant amount of time thinking about how can we put taxonomies for sabotage attacks and theft of technical data. And we looked at this from two perspectives. Each taxonomy has two dimensions: attack targets, or what can be achieved, and what would be of interest to adversary, and attack methods, how it can be achieved, how particular goals can be achieved. And as you can see, okay, nobody can read it at the scale, I understand this, but you could see that it is fairly extensive. What is really scary and worrisome is that only few elements on these taxonomies have been investigated to date. So if you want to do research in this area, you can use this as a roadmap and just pick and choose one of these rectangles that hasn't been addressed before and just do your experimental work. I also must say that since then, I would add a couple of additional elements to this taxonomy that we have not considered back 2 years ago. So obviously, we want to defend our systems. We don't want that everything is compromised. So the idea that comes to mind pretty much immediately: security is a very well-known discipline, and manufacturing as a whole has been around for decades. So we want to see how can we reuse established methods? Especially what comes in mind pretty much immediately, they are this subtractive manufacturing with CNC machine. And if you look at the workflows, which elements are flowing and how, you would see very huge degree of similarity with the workflow of additive manufacturing. And obviously, something that people could argue immediately, why don't we use pretty much the same approaches to secure both? Or can we reuse methods that have been applied to secure subtractive to secure additive? And I had numerous discussions with several researchers on this topic. And a little bit over a year ago, I received a grant from National Institute of Standards and Technology for investigating exactly this question. And we started with the knowledge, yes, workflows are similar, and the questions were, to what extent, what is the overlap from security perspective, and especially, are there some characteristic aspects in additive manufacturing security that would prevent application of other approaches or diminish effectiveness of other approaches to additive, right? And we looked at this from three security perspectives. One is exposure to attacks, ability to conduct successful attack. Another one is ability to apply best practices like NIST risk management, risk management framework. And last but not least, what is the liability in the case if attack is successful? And surprise, surprise, actually for all three perspectives, we identified both overlap and some significant differences. I was responsible for exposure part. So, and for this part, we have identified that if you are looking just at how an attacker can exploit vulnerabilities and go through attack vectors to compromise some elements, from technical perspective alone, from the methods alone, it is very, very similar to what you would see in other manufacturing technologies. This also means that if you are thinking about hardening your infrastructure, it will be technically pretty much similar to what we have seen with other manufacturing technologies. There are some differences that are more subtle in nature, but yeah. But if you go from the compromised element through what manipulations are possible to achieve effects, then you will see very, very huge differences in both technologies, even though on the surface they seem to be very similar. And that's why I argue always that we need to address additive as a dedicated security, not just as part of broader security of direct digital manufacturing. Just to give you an example on manipulations, and this is something very, very visually impressive, that in additive, you have a variety of manipulation, how you can introduce defects inside of a part, right? This is something that is unique for additive. This is just impossible for subtractive, right? In subtractive, you can only introduce defects on the surface, and such defects are easy to detect and often easy to mitigate. If defects are inside of a part, it is harder to detect, especially with non-destructive methods that currently exist. They are very limited in the case of additive manufacturing. So is there hope? Obviously. And this is a new slide, and I put it together because I'm okay. As a scientist, I always go for shiny and new stuff, and I tend to overlook the established methods, like cybersecurity. At the same time, when you are talking with additive manufacturing communities, the two biggest concerns you hear is how can we protect data at rest and data in transition, right? And this is something, or digital representation of data. And this is something what we really know how to address in cybersecurity. We really know how to harden systems. We really know how to prevent man-in-the-middle attacks. There are very well-established approaches. And that's why I would say that cybersecurity is something what is needed. We cannot solve the problem without it. But like you have seen at the beginning of my talk, not everything is cyber. Like in this side channel attack, you could bypass cyber solution just by listening to the 3D printer and recording acoustic emanations. This means also that cyber should be a part of the solution, but it cannot be the complete solution. We need to also address other parts of the problem space. And to address other parts of the problem space, we really need expertise in multiple domains. And in this diagram, you see that AM security, I just put several domains that I consider the most crucial. Cybersecurity, obviously, physical security. We need knowledge in cyber-physical systems and CPS security. We need to know mechanical engineering, material science. All this expertise should come together in a team, research team, to address challenges. So, and this also means that we need novel approaches to address novel challenges. And one of, and there are several interesting approaches that are coming. Actually, Dr. Gupta, I hope he will talk about one of the approaches to prevent counterfeit by specifically crafted design files. I think this is very interesting research. This research that I would like to present you comes from Purdue University. And I have not realized that Dr. Panchav was the leader of the team who published this research. And what I found very interesting is that this team of researchers has looked at the problem from a different perspective. And they identified that at the current state of research, we can measure properties like grain structure, right? Microstructure properties of the manufactured part. At the same time, the degree to which we can control our manufacturing equipment is not sufficient to control these characteristics. And this group of researchers came up with the approach how use this random physically random characteristics to calculate the called physically unclonable function. And this is something that you can use to, if you want to ensure that the part hasn't been infringed, you can calculate this function, you can put it in blockchain, this information path, you can send part to the customer, and then customer can verify that it was manufactured by you. This is an extremely elegant solution. Another solution that I would like to present is coming from my research team. We also looked at the side channels, but side channels not from attacker perspective, but from defender perspective. And this research is a little bit older. And in this research, we, again, because acoustic emanations from different motors can be distinguished. I will try to wrap up fast. Because they can be distinguished, you can actually generate acoustic signature of the manufacturing process. Then after you generate the signature, you can verify that the part satisfy your criteria using non-destructive and destructive testing. And if it is the case, you can say that the signature is your gold signature. And then when you are manufacturing the same part again and again, you can generate acoustic signature and compare new acoustic signature with the gold signature. And if they are similar enough, you can declare, okay, part hasn't been altered. What we have also done, in addition to generating signature, we also looked at how can we verify the quality of the signature. And we tried to break down and characterize the quality of the signature based on the thresholds, what is detectable and not detectable. This means under which thresholds we can detect attacks and above which thresholds we can detect attacks reliable and under which we cannot detect attacks at all. And based on this, we could estimate that majority of the attacks that have been conducted so far, we can detect. We have several more recent publications that improve the quality using PowerSide channel. So I will try to be very brief. Just to conclude where we stand and where we should go. So far, research community and I can blame myself too, because part of my research is going in the same direction. Majority of the research have been done on desktop 3D printer using FDM AIM process, which is good for polymers, which is very broadly spread in desktop 3D printers, to some extent in high-grade 3D printers, but also good for polymers, and to some extent relevant for composite. We need to move to materials that are relevant for safety critical parts. And this means we need to work with technologies that are relevant for metals and composites. Like for metals in powder bed fusion, direct energy deposition, way more complex machines. And solutions that we develop for PBF might not be applicable for FDM or DAD, PBF and DAD. Also, for attacks and defense measures, if you look at attacks, we need to go, and I know that we have conducted multiple attacks, and each research group tried to come up with a new category of attack. I understand this is very important. At the same time, in addition to looking at the new attack categories, we need to look at how to make these attacks stealthy. As a bad guy, as an adversary, I would want to achieve my goal, but at the same time not being detected, right? This means, and we also need to break up complex attack into the components. I call this atomic manipulations, but yeah. Also for defense measures, we need to go from the idea that we propose new approach and design attack big enough so that our new proposed approach can detect it. From this just pure qualitative idea to the more quantitative ideas that we need to identify detectability thresholds when attack can be detected or not. And both attacks and defense measures, we need to match them against each other, and only then we can really identify, excuse me, only then we can identify whether attacks can be detected or not. One category, okay, I will probably skip this slide. Okay, one thing that I want to emphasize, really emphasize, because I'm running out of time, I think, okay, we need to build multidisciplinary teams. And we have spoken before the beginning with Dr. Pancho that it is extremely important. And unfortunately, majority of teams that I have seen publishing in this area are still single domain experts. It is moving in the right direction. It is moving in the direction of collaboration between different researchers and research teams. And I think this is where we want to go, and this is where we need to go in order to solve this very, very complex problem. And I think I will stop here because I'm out of time.